Hi, my name is Brandon Hurst. This is my final project, CS 6963 Digital Forensics, summer 2014. We'll be looking at my project on RS Steganalysis. We'll begin with a quick overview of Steganalysis and, I guess, steganography, just in case anyone missed that lecture. Steganography involves concealing a message, image, or file within another message, image, or file. It's often used with encryption. Encryption, prevents an unauthorized person from deciphering the data. Steganography is used to hide the very existence of the data. There's many free software tools available to embed text or images into other images, audio files, and videos. A lot of these tools can be run from a USB drive, a CD, or even straight from a web browser, so traces of the tool might not necessarily appear on a hard drive search. Steganography has been used in recent times by Al-Qaeda members as well as pedophile rings to try to hide their activities. Some corporations are beginning to even worry about the insider threat exfiltrating sensitive information using steganography. I think they already have some appliances on the market to help with that. So discovering which files might have embedded data in them is the first step towards either decoding that data or revealing people's intentions. Oftentimes this is referred to as the passive warden scenario, not changing anything but just observing basically and trying to figure out what's going on. So one of the most common methods of encoding data is by altering the least significant bits of a noisy image, sound, or video file because the human eyes and ears aren't as perceptive of those gradual changes that the substitutions introduce. LSB isn't the only method, but it's one of the most popular, so that's what we're going to attack here. So how do we detect this kind of LSB alterations? One method, as the title may have tipped you off, is RS Steganalysis. I'll give a very high-level explanation of it, but if you're interested in getting more in-depth, there is a paper that are mentioned multiple times in the report, as well as the code. It's reliable detection of LSB steganography in color and grayscale images. It is a statistical method which partitions the image into many small groups. Each group can be classified as regular or singular, R or S, depending on the smoothness, I guess you can't see my air quotes, of the pixel values of this group versus a partially altered version of the group. So a couple things we'll define, what is smoothness? We create this discrimination function which quantifies the smoothness, and it can be as simple as taking the delta between neighboring pixels and summing all those up for the group. The other thing, a partially altered group, what is that? We accomplish that by creating a mask that alters some of the values in the group and leaves others alone. So a regular group would be one that starts out fairly smooth, but once you alter some of those values through the mask, it becomes less smooth. So you're comparing the altered group to the unaltered group for smoothness. So we look at the percentage of those regular and singular groups for a positive mask and a negative mask, which is basically the negative of the positive mask. We then flip all those least significant bits in the group, 0 to 1, 1 to 0, and take those percentages again. So in the original group, if X% of the bits were flipped from the original image or the original data stream that you had, if you flipped X% of them as part of your embedding, then when you flip all the LSBs, you'll actually be at 1 minus X% in the new group. So that sort of gives us 4 extra data points. Let's see. There is a curve here from that paper that I mentioned, and it basically shows the regular for the positive mask and negative mask, singular for both positive and negative mask. For the p over 2, just if you embed a message of length p, on average you're going to flip half the bits, so hence the p over 2. And then your other 4 data points are for that 1 minus p over 2, that's where you flipped all the LSBs. And it turns out that these RNS curves are quadratic in the amount of data that's been encoded, so we can use these 8 points along with some assumptions to estimate the amount of embedded data in the image. So you're trying to figure out where is that P over 2, or I guess more accurately P. You know, if you're detecting P over 2 flipped LSBs, then on average the message length is P. So that's what you're trying to find along that x-axis being the percent of embedded data. A note being, if you tried to fully embed data throughout the whole image, you'd be at 50% because you would have flipped half the bits. So if you followed all of that, good for you. If you didn't, don't worry too much, but there is a short quiz at the end of the video. Kidding, obviously. It really isn't critical to understand the math of this, and if you really want to get into it, you probably need to read the paper. The only things to really take out of this are the concepts of the mask, which selectively alters the pixels, and the discrimination function, which is just a way to quantify the smoothness of the group, because those two concepts will come back later. So now we can dig into the code a little bit more. So I guess we'll start by going through the first couple paragraphs here. The script has 5 main functions available from an interactive menu. It will analyze an image. Currently only 24-bit color PNG are like the quote-unquote officially supported, but it does mostly work with bitmaps as well. However, I have seen some bitmaps crash the program, which is why I'm only saying PNGs right now. So analyze an image, it'll run the RS Steganalysis on it. It'll display an estimated percent of the image, which contains hidden data, as well as the corresponding number of bits and bytes that are estimated to be hidden. Another function that it has is to compare images. So you can basically give it 2 different images as inputs. It'll create an output image based on the differences between the two. So that's great if we have a cover image and a stego image. We can see how that data was embedded. An LSB image basically looks only at that least significant bit of the image. If that LSB is 0, then that color is 0, and if the LSB is 1, then that color goes up to the full 255, just to amplify that. It's also an interesting tool for looking at some of these images. Another one, analyze folder, takes a folder as an input and basically runs each one through that analyze image. Then it generates an output text report, a CSV file, and an SQLite database of all the file names, locations, resolutions, the percent of embedded data, and whether that exceeded the threshold or not, which is currently set at 3%. Lastly, analyze disk image number 5. So this one as an input would take a disk image, and it uses the sleuth kit, TSK recover, to pull all the files from the image. It then goes through, deletes any files which are not a supported type, currently just PNG, and passes that folder along to the just folder analyze function. So dependencies, it does require the OS, argparse, systime, SQLite 3, subprocess, and PIL. In addition, if you're going to do the disk analysis, it requires the sleuth kit in order to do that TSK recover. You don't need the TSK recover if you're just doing folder analysis, image analysis, compares, that type of stuff right there. So let's go through the code a bit more. So here we're just importing all of the different modules and stating if they aren't there. So discrimination function. This was one of those things from the RS Steganalysis that I said would come back, and here's the first part of that. So there's multiple ways that we could calculate that discrimination function. How do you quantify the smoothness of a group of pixels? So here I'm showing 2 different ways of doing it. Basically, this top function goes across the rows and compares 1 pixel to the next, and then goes across the columns and compares 1 pixel to the next. This bottom version of that function only goes across the rows. So it's two different ways of calling things out. We'll go down, mask the box. This is basically what just takes that group of pixel values and a mask, applies the mask, and gives back basically the new group that has had the mask applied to it. Break image, this function takes an array of pixel values and returns the group based on the position, so just how you go through and pull out the groups of pixels. So rather than, I guess, read through all of these different functions, I'll just hit up some of the more interesting ones. Let's see, here's where a lot of the math goes down. So here's a good one. Analyze folder. So this is where we get into actually analyzing a folder. There's a file types here at the top, and you'll see that the only currently supported one is PNG. There is a bitmap there, and I have used it with bitmaps, and it usually works, but occasionally a bitmap will crash it for reasons that I haven't really gotten into. So I've commented it out in favor of usability over functionality, but if someone really wants it, the bitmap, basically just by toggling that, you'll when you analyze a folder, it will try to analyze bitmaps. And there's some other file formats that it would be nice to add at some point, but that's for a later date, I suppose. What else is worth noting? In here, here's where we're writing CSVs and SQLs, some of the individual functions. Here we go. The cleanup file. So if we ran that TSK recover and we have created an output of all the files on a disk, we then go back through and basically delete the files that we don't care about. This is also set to PNGs only for same reason. I suppose if I were a better programmer, you would only have one instance of this, but alas, there are two. What else? We jumped back up. Sometimes the virtual box doesn't like the mouse scrolling. All right, here's another interesting point I'll touch on. In my little run interactive kind of start of the menu here, I've got some things I'm defining. One of which is these masking boxes. Talked about the mask before. This is the other item. So I've got 10 different masks defined here, and I've actually gone through the analysis on all 10 of them, and maybe it makes sense to look at it in a little different fashion. So the mask is just basically the group of pixels that get analyzed at a time, and these permutations that happen to them. So I basically went through these 10 different masks and tried it out. Turns out one of the simplest ones is actually one of the best. Just a 0, 1, 0, compare three pixels at a time. So going back to the code, what else is interesting? So discriminator overlap is currently set to 0. What this really means is when we go through and pick out those different groups, do we want the groups to overlap each other? Right now it's set to false or no, so one group will be adjacent to the previous group. It won't overlap at all. If this is set to, let's say, 1 or true, then when it runs through, it'll actually take the next group will just be 1 pixel over from the previous group. So what that basically means is it'll end up being 3 to 16 times slower depending on the mask used. 3 times if the mask is 3, 16 times if the mask has 16, because because it overlaps instead of non. So you do get a little bit better results performance wise, but there's a pretty big time hit to it, so I've turned it off because I'm not quite sure it's necessarily warranted. Let's see what else we have going on in here of interest. So here's the analyzing a folder one, and at one point I was going through and basically rerunning that folder analysis with every single mask, all 10, and it's since been commented down so that it's only using that one that I've deemed to be the best for my analysis of the images that I've done. So the default, once again, the masking box 1 goes back to that 010 was the best performing one, and so that's also what gets used in the analyze a single image and everything else. So I think that's pretty much the end of the program. So rather than talk about it, I suppose we ought to just run it. Python rs steganalysis.py. So this is our menu here with our 8 options, but I guess before we dig too much into this, let's go back and look at our cover images here. So these are the images that were used in the for the program. I picked just 8 images of various complexity. This would be a fairly simple one. A little more going on. A little more. So 5, 6 is a boat. 7, fairly elaborate bridge, and then 8 is a, extremely, I don't know what you would call it, but there's a lot going on in that star image right there. So those are 8 cover images. I guess we should also talk about the payloads that we're embedding in these cover images. We've got 3 text files that I created early on. So I've got a short text, which is just an email address, donjoe@gmail.com, monkey123. It's all of 27 characters. A medium text is the U.S. Constitution, 26,000 characters, and then a long text, Alice in Wonderland, 160,000 characters. So those are the payloads that we are then embedding in these cover images. So I guess let's talk about encoding the payload. I've used 5 different algorithms for the 3 different payloads. So let's switch back to the program now that we've got running. So I've already embedded some of these payloads in the cover images, so why don't we do a compare number 2, and it'll basically ask what are the names. One of them's dog.png, the other one will be dog, medium, stegpy was the thing used. So it's going to ask me the location, but you can already see basically what's going on here. It compared the 2 images. You can see about 20% of the top pixels have been altered, the least significant bits of those. We'll just call it dog, medium, stegpy, compare. And now we've got a compare file that is that image that we're looking at right now. So we just saw what one of those embeddings look like. Let's take a look at all of them. So we've got a few. So I used 5 different algorithms from 3 different programs to embed all of my payloads into my cover images. So one of them was Steganalysis.py that was actually from a Sci4 module from our own Mark previous semester without the key, and you can see it's just a linear embedding from the top Also, there's links to where all of these steganography tools can be found in the report as well. So that's the first one. Second one, this is that same stegalize.py with a key. So here you can see it's no longer linear across the top. It's kind of spreading it throughout. The key is basically just the seed for a pseudo-random number generator that picks the next pixel. Now, because of this, I didn't use this methodology to insert the long.txt payload into the cover images because of the way this pseudo-random number generator picks the next pixel to embed into. It caused the embedding to become significantly slower as that payload size approached the capacity of the cover image, because there just weren't that many free pixels. So for this one, it only did the small and the medium. Next is a steganogra.py. You can see it's another linear embedding from the top. Next is a steganography studio with a blind hide embedding from the top. And I'll toggle between the two, but it's interesting to note that they are, not the same at all. And even if I go back to that stegalize.py, all three of them have slightly different embeddings for various reasons. So going on to the fifth and final one, the Steganography Studio Battle Steg. So this one actually uses an edge detection filter to try to embed more in those regions with large pixel variations to reduce the perceptibility of the LSB alterations. So I've got one, slightly more complex embedding algorithm, three of them that are fairly straightforward, just linear, and then one that's a keyed kind of random throughout. So it seemed like a good kind of cross-section of LSB embedding. So let's take a look at what the LSB looks like. Let's go back to our program here. So we just looked at the compare images. Let's take a look at the LSB image. Let's take a look at the tux. That was the Linux penguin. You can see, you can sort of still get an idea what that image was just based off the LSBs of that. A lot of uniform areas. That would be one of the simpler images. We'll call this tux lsb.png. And then let's create another LSB image for one of the more complex ones. That's star.png. And you can see this one is just all over the map. There's nothing of any significant use to us here. And this is just the cover image. There's nothing actually embedded in this, and this is the level of chaos that you see in that module. So let's do an analyze image now. We'll go back to that dog medium steg py.png. So this is that dog image with the medium text, the Constitution embedded in it. We'll run the analysis. So it tells you that the image size is 640 by 528, a mask of 3 by 1, and then it basically runs through red, green, and blue. Gives you a count so far, tells you the percent of each of them likely encoded, and then basically takes an average. It's saying that roughly 20% of the least significant bits have encoded image in them. It tells you the number of bits, the number of bytes. And if we go back and look at that compare, about 20%, and it looks pretty close to that is what we're being told. So that's nice. That's our analyze an individual image. Why don't we analyze a folder now? There's a test images folder. So this will take a little bit longer. So there's that dog medium steg py that we just looked at. It also, I put in another image at 25% resolution, at 50% resolution, and then at 100% resolution of the original one that I looked at. And the reason that I did this was because one of the things I've noticed is that as images get smaller in resolution, they tend to have higher percentages of that estimated hidden data, which sort of makes sense. I mean, ideally a cover image should show up as 0, but it doesn't. There's a certain amount of sort of randomness or chaos in there. And I guess if you have a image with a higher resolution, then you've got more pixels. So each pixel group can be more uniform. The color is going to change more gradually. When you get to smaller resolutions, you got to have a greater pixel-to-pixel variation to cover that, which is why the RS algorithm picks up a little bit of that as embeddings, sort of false positives. So you can see when you get up to decent image sizes, just getting through all of the analyses isn't exactly speedy. When I was doing big folders, and then not only big folders, but running through multiple different masks on these big folders, you know, it was certainly a run it overnight kind of program thing, not a necessarily sit and wait. Although this shouldn't take too much longer. So it's going to run through, and then it's going to give us our text file, it's going to give us our CSV file, and it's going to give us our SQL file. Why don't we go ahead and where am I at here? While that's running, I'm going to just go back. And we'll do is it 3? So finished reds, now it's finished greens, working those blues. After this, we'll run it on an image, a disk image, which, you know, the functionality is there to run it on a disk image, but when you do run it on a disk image, what'll happen is you'll end up picking up a lot of browser thumbnails and cache items, a bunch of 1x1 pixel iframes, which luckily no longer crashed the program, but did initially when the thing ended up with 0 groups. Didn't quite know how to analyze a single pixel, but that's been taken care of. Probably should have made my own disks for testing that functionality, but I ended up just going to the Digital Corpora website and pulling one of theirs. So I think this is the last image in this folder, half the resolution of the last one, so it should be, what, 4 times faster than the last one. So I guess jumping ahead a little bit, we'll start thinking about some of the results, even as we're still running the program. For anyone keeping track at home, there's 8 cover images, and each of those images gets embedded with 3 different lengths of text by each of 5 different algorithms. So we've got 120 images in our folder that I've been analyzing when I go through the full run. Okay, so we've successfully written those outputs. Let's take a look at that, and then we'll do it dot dump Steganalysis, and it basically is giving us all those values. I think I'd rather look at it from the text file though. So when the Steg report was created, the mask box used, and then that dog medium Steg PY that we put in there, the one we looked at that had about 20%, says this image likely has hidden data. And then you can see the full resolution image is at 0.0097. When we cut it in half, it went up to 0.010. And then when we went a quarter, it went up to 0.02. So you can see at 2300 by 3400, less than 1%, at half that resolution, around 1%, and then when we halved it again, more like 2%. Kind of interesting. And then also a CSV file. And I guess I should go ahead and start analyzing that disk image, so we don't have to waste any more time. So it basically tells you launching the TSK, the sleuth kit to recover the files. This is a decent size disk image. So now it's deleting all the non-PNGs in that recovery folder. It'll also go through and delete empty folders, and then it goes through, and because a lot of these are low resolution images, it blows through them pretty quickly. But it was a decent size, 170 megabyte disk image file, which I guess is not a big file by today's standards, but you know, big for just doing testing on. What were we looking at? The CSV file was the one we had not done, and let's see, what am I looking at here? The first one versus the one that just completed, although I guess we could have looked at either of them. Is that not opening anything up? So there we go. Here's our comma separated value. It's basically just the mask, the location and file name, resolution, percentages, and then whether it's deemed to have the hidden data or not. And I've got 3% as my threshold set right now. So what did we say? We're at 120 images, which is our 8 cover images, 3 lengths of tests by 5 different algorithms. Then we've got our 10 different permutation masks by 3 different discrimination functions. So we've basically got 30 different analyses methods on those 120 images. So there's 3,600 analyses that are covered in this report. So for each of those 30 analyses combinations, there is a let's see here. There is like a table that came out. We'll just look at the PDF version of that table. So what we're looking at here, the first column is just the cover name, cover image and resolution. Second column was the cover image percent of embedded data deemed from the program. Now ideally, every single one of these should be 0%. None of them are. 4 of the 8 are less than 1%, 7 of the 8 are less than 3%, which was why 3% was set as my detection threshold. But you'll notice that star one, that kind of computer-generated weird geometric pattern, is up around 15.3% as just the cover image with no embedded data that I know of. And it's a fairly intricate, and because it's computer generated, it's probably got more color transitions than most natural images, but images of this style will set off detector false alarms. They could be included amongst actual Stego images to draw attention away from the real hidden data. Column C, that's just our 5 different algorithms that we used for embedding the data. D through F are the percentages that they were after embedding that data, and then the following 3 columns are that delta between the cover image and that. So you'll see for that short text, it's in the noise. A lot of times it actually went negative. That's how minor, you know, something of just like email and username are. Medium, you get up to actually a decent run of detectable amount, and same thing for long. So one of the kind of interesting things to look at is that there's quite a bit of variation even just between the different tools. I mean, theoretically, these are all embedding the same data in a column here, yet you'll see 6% up to 18% detection. So that's just the detector isn't perfect, and some embedding methodologies fool it better than others. One of the other interesting things to note is that some algorithms, you know, that battle steg that looks for the edge detection did pretty good on most of the medium text. You can see it's at less than 14% here, whereas the other ones were above 20. So it did a pretty good job of hiding from that RS technique. Whereas when it came to the long text, it actually was one of the worst. It's at 82%, even though others are in the 39 to 62 range. So there's not really one best technique. It really is dependent upon the cover image and the amount of data and everything else. So that's kind of interesting. So each of the three different tools that were used, the Sci-Force Stegalize, the Steganogra PY, and the Steganography Studio, each detect their own images, and in some cases can even try to brute force a key value and to recover the payload. They can each do their own, but none of them can do any of the others. Even the ones that were all linearly embedded, when you try to have them pull the payload out of someone else's stego image, it either just comes up with an error or it just gives you a bunch of gibberish. So they're really not cross-functional. Versus the RS detector, it's not as good. It doesn't give you the actual data that was embedded, but it works across all the different ones as long as the amount of embedded information is large enough. It would have been nice to have had a few more data points between the short text and the medium text, but I was already, 3,600 analyses, and it is what it is. So that's one of those things for future work, which there's some different things that would be interesting to look at. It'd be nice to be able to process some additional file types, particularly JPEGs, but the lossy compression is a little bit different. It would be interesting to try a bunch of different resolutions, larger and smaller, and look at how the results change with resolution. It might even be possible to compensate for that in the percentage calculation. As I mentioned, having more increments, maybe every 5% instead of fixed lengths. If you did 5% of each one of these, it would be a little bit better apples to apples comparison. And then just having a lot more data points between the short text and the medium text, since that's where the differentiation's really going to be. I mean, the way it worked out, none of them could detect the short text. All of them could detect the medium text. It would be nice to have had some more data points in here to differentiate. Finally, adding additional Steganalysis algorithms like the sample pairs, the chi-square analysis, discrete cosine table analysis, if used in conjunction with the RS, could certainly increase sensitivity and or decrease the false positive rate. So that would be other things to look at in the future. But that is RS Steganalysis in a nutshell. I hope you enjoyed. Sorry it's so long. Brandon Hurst signing off.